Hi everyone. So let's get started with lecture 6. So in this lecture, we're gonna look into some additional development using duality, which was the theme of our last lecture. In specific, what happens when we look into modifying problems that have been solved by adding constraints, by adding variables, and then by changing the input data in any way. And we'll see that these have a relationship with what we see in terms of duality and in specific the dual simplex method. Then we're going to look into the notion of cones and extreme arrays. And basically because there are two important things associated with problems that can go wrong. One of them is that we can use duality and the notion of extreme arrays to identify unbounded directions in our model, which can be useful in several contexts. And then we're going to look into this very important theoretical result called the Farkas lemma, which allows us to generate infeasibility certificates for our LPs. And then we're going to finalize talking very briefly about the resolution theorem that uses some of the concepts related to extreme arrays. And also because the resolution theorem is going to be one of the stepping stones to develop the more sophisticated methods we're going to talk about at the end of the course. But let's get started. In this video, we're going to be focusing on the first part here, which is generally called sensitivity analysis. Right. So the idea is that we now have solved our problem P, which is written in this standard form that we've been seeing. And we have this optimal solution that I'm calling X bar, which satisfies the optimality conditions we've seen before. There is, we have a feasible solution. Everyone is non-negative. And our reduced costs, they are all positive because, non-negative even, because we are minimizing. Okay, and then what we want to look at is to see what happens when we start messing with the problem once we have solved it. And when I say by messing is that kind of try to figure out what happens with these optimality conditions once I start to make changes ex post after I solved it to optimality. So we're going to consider 4 specific cases. The cases where we add variables and constraints, because these are going to be important for the development of the methods we're going to see next in the course. So basically, this is related with the method that we use to solve non-mixed integer programs. And this is going to be relevant when we look into a method called column generation later on. And these are the two more classic sensitivity analysis. So basically you are at the optimal point and you're trying to understand what are the consequences if the data you consider in your optimization process happen to be slightly different in terms of the independent costs or the coefficients. What we're doing here, we're not going to look into the variations associated with A, but you can construct a similar kind of approach to try to understand what are the permissive changes you allow in A. We're gonna leave them as an exercise, and there is some information on that in the textbook. But we're gonna concentrate on these two classic ones because they seem to be more relevant to what we're looking at. Right. So in the case of adding a variable, what we're gonna assume is that we have this variable x n plus 1 with a respective column associated with it, so a coefficient c and a collection of coefficients a. And that means that we are going to augment our problem to now have this additional part represented by these. Okay? And we want to understand how does that affect the optimal solution I found for my original problem P when xn plus 1 was not added. So you can see that what we actually have to do is to figure out whether the basis B, that was the optimal basis for P, is still optimal. Because if adding this variable doesn't change anything in terms of the optimality of the basis we have at hand, then the optimal solution is basically say that this new variable has value 0, and it's exactly the same optimal solution that we had before. The interesting thing happens when you calculate the reduced cost for this new variable, and then you figure out that there is an optimality condition that, that is became not satisfied. In other words, you look at the reduced cost of this new variable, which is given by Cn plus 1, Cbb minus 1, and then the column associated with a new variable. And then when you look at this, you see that you have a reduced cost that is negative. Because then if it's the case, it means that the addition of this new variable gave you a new direction in which you can further improve the objective function, which is desirable. And that setting then is perfect for primal simplex, because what you're going to have is a fully optimized tableau, or a fully optimized basis if you wish. So you have a starting basis B, the optimal basis for P, from which you can start and do, say, another iteration of the primal simplex and perhaps find optimality. That iteration will be considering making this variable new variable basic. Okay. And that's obviously more efficient than just resolving the problem from scratch. So you can use primal simplex with a warm start, as we call, to do a few iterations and perhaps find your optimal solution. The case when you're adding a constraint is a bit more complicated, and it's just because the addition of a constraint changes the size of your basis, the basic matrix, right? So let us suppose now that we have this new constraint. So we have this, now it's like I'm adding a row to my matrix A, and the constraint is like such, and I'm adding to P. So if my current solution satisfies the constraint, then there's nothing interesting happening, because that just means that this is a redundant constraint and nothing is going to change at all, right? The interesting case is the case when this constraint happens to remove the current optimal solution. Remove in a sense that the current optimal solution is infeasible in terms of this constraint. So graphically, it kind of looks something like this. You have a constraint like so, and then you have another constraint like so. And suppose you found your optimal solution here, x bar. By removing, we mean that we are adding, say, this new constraint like so, wanting everything that is in this direction. And notice that this point does not satisfy this constraint anymore. So we say that this constraint is removing x bar. That is the interesting case. The less interesting case I was on about is when this would be, say, that. So it doesn't change anything. Green is just a redundant constraint. So how do we go about if we are in this second and more interesting case when this is so? We gonna do, well, first thing, we add a slack variable to that constraint with respective negative sign. And then we go to change our matrix A, which is going to be augmented. We can call this matrix A bar, which becomes the original matrix A. For all the previous rows, this variable, this slack variable was not involved, so we get 0. That is the element associated with this constraint, so the new rows of A, accordingly, of course. And then this is this coefficient -1 there. Okay. So with that new way, we can form this new basis B, which is the original basis B, everything 0 there. The respective components from this, they are associated with the basic variables for B, and this is this A. So A is a subselection of the coefficients in this vector AM plus 1, where I'm only picking those that are part of associated with basic variables. And then the -1 is just the value associated, is this coefficient there. Okay. Because we know that this is the case, we can easily derive our inverse of B bar, which gets this form here. A easy way to see that is just to see that if you do the matrix multiplication of these elements, you get exactly an identity. So you get the identity matrix there, and for the other outside terms outside the main diagonal, you get zeros. So do the exercise of multiplying, pre-multiplying or multiplying b with b minus 1, and then you get exactly identity matrix and then 1 here. So that's our b minus 1, right? And our basic feasible solution associated with b is simply the original solution x and the value of the new slack that is added there. So it's this term here is simply this moved there and this moved to the other side. So you get xn plus 1 equals this minus this at x bar, of course. So basically what you're doing is when you add a new constraint, your basis is increasing, and this new position in your basis is filled with the slack variable of this new constraint immediately, because that's kind of a trivial way of doing so. But you might notice that that slack variable will have a problem, because if this is the case and we're talking about the slack associated with this constraint, for this solution, this slack is negative. So it's a non-feasible, it becomes a, so we say a BFS, but it's not F anymore. It's feasible in a dual sense, but not feasible in a primal sense. So we can see that. So the reduced cost, if we calculate the reduced cost for the new basis, so this is C minus CB. This matrix is the B the inverse of B bar, and this is A bar. So the vector of reduced costs look like so. And you can see that the new variable gets a 0 reduced cost, meaning that this vector satisfies dual feasibility conditions. So this solution is dual feasible. All the coefficients here are non-negative, because this was the case already for P before we added the constraint. And that kind of, the power of your brain that is now associated with dual simplex must be tingling now, because this is kind of like looking, wait, I got this new solution is automatically dual feasible, so it looks like dual simplex could be of help here, right? And it's actually the case, and it's truly the case. So B bar is initial basis for dual simplex. So you don't have to re-optimize again from scratch. You add the constraint, you do this rate transformation, and that starts doing dual simplex iterations. And that is, by the way, the mechanism behind the methods we're going to see for integer programs in a couple lectures. That's the reason why you can implement efficient solution methods for integer programs, because this re-optimization step can be doing really fast or really efficiently using dual simplex. So to build this initial solution, what we do is basically just doing an additional row. And if in order to be able to see that in kind of a tableau notation, we can think of how the b minus 1a changes. So if I think of b minus 1a, b bar minus 1a, or the inverse of b bar a, what I get is this. So it's basically the original tableau, and then I'm adding this column with zeros, and then I'm adding this new row to my tableau with a coefficient 1 for the column of this is my x. Well, this is the slack m plus 1 that I added, and this is its column. Okay, so you can immediately change the tableau as well to carry on and do a dual simplex iteration. And just an important remark, there is an obvious relationship between primal and duals in this. So adding a variable to the primal is the equivalent of adding a constraint to the dual, and vice versa. So you can use the same technique one way or another, depending on whether you're talking about your primal problem or your dual problem. So the self-dual property kind of can be used here as well to let us do this symmetric analysis. So here is a numerical example explaining what's going on. So basically what we have, first let's look, we're gonna use the same problem throughout all the transformations we do. So it's this minimization problem with these two slack variables. So it was original like so, and then we added positive coefficient slack variables with positive sign. And then we optimize this and we get an optimal solution that is x12, x22, and this is the tableau for the optimal solution. And let's assume that once we optimize, we want to add a fifth variable for which the coefficient is -1. And it's a variable that has coefficient 1 and coefficient 1 in both constraints. This is actually anyway, we'll talk about that later. But this is kind of like the form we have when we're looking into the context of column generation, which we'll talk about later on. So what I do is I first calculate a reduced cost for x5, which is given by this, and turns out that it's -4. So it means that it's negative. So I'm really interested in having this entering the basis. And by the way, b -1 a5 is given by that. I'm gonna need that when I augment to my tableau. So just one thing that when you're using tableaus is that because my original variables x3 and x4 had associated with them an identity matrix, and this whole thing here is b -1a, that means that this is b -1. Let's put it here. I don't know. Let's call it a original and a matrix I. Okay. So this thing here is giving this part here is this b -1 original, because my b now is composed by my original columns times b -1, my b -1 times original columns, or my b -1, which is the inverse of my current basis b, is formed by variables 1 and 2. So I get 3, 5, 2. Oh, sorry, you can see that 2 and 3. Let me move that here. There you go. So when this term here is basically b -1 times b, which is formed with the original variables. So that's why I get an identity here. And because my original here was an identity, when I do b -1 these, what I get is just b -1. So the tableau has this interesting property that the terms below the slack variables, they give me the inverse matrix at all times. So, and multiplying this matrix by the vector 1, 1 basically means that I'm getting 1 times this column and adding to 1 times this column. That's what means multiply this matrix by this vector, right? So I get 3 minus 3 plus 2 minus 1, and 5 plus minus 3, 2. So that's how I could get this. Or if you don't like any of these and you have Julia, and you just, okay, my basis here is x1 and x2 clearly because they are here. So I'll just go get the matrix 3, 5, 2, 3, invert that, and you're gonna get this. As if you have an inversion available. The tableau was useful in a time where we had to do exams by hand, and you didn't have access to a calculator that you could invert things. So knowing these tricks were handy. But there is no practical implication other than allowing you to do hand exercises. Anyway, so yeah, we did that. And now our problem then becomes this. So we add the variables there. The coefficient is -1, 1 and 1 here. So this is our new problem. And then when I look at my new tableau, what's going on here is that I added a new column. This is my b -1a5 that I just calculated. This was the reduced cost I calculated to see if it was optimal or not. And that, you can see, is a tableau that is screaming for primal simplex. Make this my column, select the column, then my ratio test to see which one is going to leave the basis, and so on and so forth. Okay, and that's it. Now, in the same example, let's think of the case where we add a constraint. So I optimized again, same problem, same solution, and then I added the constraint x1 plus x2 greater than or equal than 5. That is a problem because x1 and x2 is 4, plus x2 is 4, and 4 is not greater than 5. So this removes, in the sense we discussed before, the current solution. So how do we deal with that? Well, we know that our am plus 1, like we defined before, is 1, 1, 0, 0. So here it is. And this term here that's going to become the row of your simplex tableau is this a, b minus 1a. A here is the components of this thing associated with the basic variables. So a in this case is just 1, 1. Sorry. 1, 1. There you go. Okay. My current b minus 1 is this. My matrix A is my matrix A, the 3, 5, 2, 3, 1, 0, 0, 1. And so this is what I get from here is a vector with 1 row and 4 columns. And this is sorry. Let me just think my row operations here. So this is actually, yeah. So this is a vector with 1 row and 4 and 2 columns, and 1 by 2, 2 by 2. I get a 1 by 2 vector. A 1 by 2 vector times a 2 by 4 matrix. I will get a 1 by 4 matrix, a 1 by 4 vector. And this is originally a 4 by 1 vector, which I make 1 by 4. And then I get a 1 by 4 vector that looks like that. Okay. You can redo your calculations, but this is just selecting the basic elements from this thing, which is this. Right. So that would be the row in our tableau that is going to pop up here, right? So in order to add this constraint to my new problem, the first thing I do, remember, I multiply this by minus 1, and then I'm gonna add a slack variable there. So I get something that looks like this. So here it is, my original problem plus my new constraint. This is that part of the tableau associated with the original basic variables, the original variables. My new slack is assumed basic in this new basis. So my basis was just 2 elements, now becomes 3 elements. Sorry. 2 elements now become 3 elements. So my 1 is here, 0 for everything else. And then the last thing missing is this minus 1 here, which simply comes from having minus 5, minus 2, minus 2. When they move to the other side, I end up with minus 1. And if you look at that tableau is screaming to be solved using dual simplex because it's dual feasible, it's primal optimal, but it has a primal infeasible variable right there, which is the slack of that constraint because it's on the other side of the constraint we just added. And that's it. All right. So here it is how you can add constraints and solve, hopefully a few iterations of the dual simplex will be enough to get this optimal again. So you don't have to iterate from the beginning, and perhaps redo some of the iterations we just done. Right. So now in terms of the changes of elements in your input data, there's basically 2 of them that we are interested. One of them is when you have your right-hand side. These are also called independent terms in some contexts. They change. So I'm assuming that one specific element is being perturbed by a value delta. So being made smaller or larger by delta. So what we're interested is the range within which B is going to remain optimal. So that basis won't change. And obviously, your optimality conditions associated with that basis are not influenced by your B term, because they only depend on the coefficients of the objective function and the current basis you have. So that means that you only have to make sure that what is affecting your what what is being affected, what you have to make sure is that the feasibility, which is what being affected, is maintained. So that when I look at this term here and it being added to my B, this thing doesn't become negative. The story, it goes like this. It's because you have, say you have a constraint like that and a constraint like that, and this is your optimal point here. So when you're changing the position, when you're changing B, what you're actually doing is changing the you're just translating this. Let me draw a third constraint here for this picture to make sense. So basically what's gonna, suppose we have a third constraint like so. Okay, when I start changing the position of this constraint, so this basis, I decided that this basis formed by the intersection of these two orange lines is optimal. So when I start moving it, if I move it this way or that way a little, I'm not changing the optimal. It's still the optimal basis, so it's still the intersection of these two lines is the optimal point. The problem is, as soon as I try to move it too far away, like here, this is probably still optimal, the best combination I could do. The problem is that it's not feasible anymore because, now this constraint in blue is not satisfied anymore. So it means that my actual optimal basis will have to be changed because that basis, though is still the best, is not feasible anymore. So that is what this is saying basically. So, and in order to assert that, it's not that complicated. Basically what we do is, noticing we have to do this by individual elements, one at a time. So we have the independent effects of each of them. So basically what we're doing is if you think, remember that this is the ith vector, so 1 for the row you're interested in, 0 for everyone else. So b minus 1b is fine, but when you do b minus 1 this term, what you're actually looking into is this, if you get g being this ith column of b1, that means that you're interested in changes in exactly, caused by the variations are going to be influenced, we're going to appear in that exact column. So b1 minus b is just xb, and then what you're saying is that xb delta g has to be greater than or equal than 0, which means that this has to hold component-wise. This is obviously component-wise as we're doing. So basically what we are doing is we are looking at that column of bi and looking at each of the row terms and trying to guarantee that this is the case. And this is going to be just a game with the signs of these elements in G, the elements in G, basically. Whenever G is negative, you have to make sure you're getting the minimum of them. And whenever G is positive, you have to make sure you're getting the maximum of them because this is going to the other side. So basically you're having minus xb divided by G. So when G is positive, it means that you're looking at the negative values, and the negative values you have to pick the max, and when G is negative, you look at positive values and you get the min. So that's the range, it's that story that you have things, suppose my 0 is here, and then you have, limits coming from this side, so you have to get the min for positive things, and limits on that side, then you have to get the max. And that's just that. So that's what's going on here. We'll have a numerical example of that coming in a minute. So if this makes more sense for you, it might make more sense for you if you look in actual numbers. Here it is. So basically what we're doing is we're looking at our problem again, and then what we're going to change b1 by delta. And remember, b1 is associated with this constraint 3x1 plus 2x2 plus x3 greater than or equal than 10. So this 10 is what I'm looking into varying. So I know that this is my b minus 1 matrix for which the first column is that. And remember, I'm looking at the first column. So basically, what I'm doing is looking at this plus this times delta greater than or equal than 0. And so let me put this. So this times this plus this times delta greater than 0, which is here. And this times this plus this times delta greater than or equal than 0, which is here. And then what I get from this one, I get the delta has to be less or equal than 2/3. And from this, I get delta is greater than or equal than 5 minus 2/5. And, you know, this is because they are in the, I just have one positive, one negative. The min and max are themselves. So this is the variation in delta that is allowed such that that base remains optimal. We can also, you know, within this range, we can also see how the objective function change. Of course, if I'm moving the constraint, the value of the objective function will change because I'm moving the point at which I'm sat at with the optimal value. So so this causes a change in the value of the objective function, but it's also easy to predict. It's basically the delta variation on the vector CB, on the components of the vector CB associated with the variable you're looking into. Remember that this is the vector that has 1 for the variable of interest and 0 for all the others, or the position of interest. And we know that if we look at P being such, there is a B minus 1 missing here. There is a B, an inverse of B missing there. Sorry for that. That makes sense, right? Because then this is gonna become let me get a color, different color here, because this is gonna become CB B minus 1B, which is C transpose X. And we know that B minus 1, CB B minus 1 is our dual variable P, like we saw last time. So we can use the dual variables to infer that this is exactly this value of my original objective function from strong duality. But this is showing kind of the interesting part, basically telling us, like we saw last time, that P is indeed a marginal value associated with the variation of the term BI. And what I'm getting in my objective function is the value of the dual variable times my delta term there. All right, so this is connecting with what we seen last time of the interpretation of the dual value. And finally, if delta is outside the feasible range, then the solution is going to become primal infeasible, because that's the condition we are enforcing. And if it's primal infeasible, the recommendation is use dual simplex to see what's the new value. So basically, it's the same effect of adding a variable, in the sense that you end up with this, when, you know, looking at the picture I drew before, you're moving too far away, so that current basis, even though it's really good, it's dual feasible, it's not primal optimal anymore. Oh, sorry, it's not primal feasible anymore. So that means that you have to do a dual simplex iteration to find a new optimal basis that is also primal feasible. And the last type of changes is those those that happen in the vector C, the coefficients of the objective function. So likewise, you get in a coefficient of the objective function and try to change it by delta. So in that, if you're changing so basically two cases can happen. The first case is the trivial case, let's put it this way, when you're making changes in a variable that is non-basic. So if the coefficients are changing in a variable that is non-basic at the optimal, the changes they can only be such that you don't flip the reduced cost. So your optimality condition is that condition to say that all reduced costs are positive. So we stopped there because all your non-basic variables had positive, no negative reduced costs. But if it's so that, you know, when you're making this perturbation, you get a you make your reduced cost flip sign, then that base is not going to be optimal anymore. So it's just the optimality condition. That's why he's saying that it's if the single condition is just the optimality condition associated with that specific reduced cost for that non-basic variable. And the variation is the minus the current value. So if it's currently 2, the change is minus 2, because more than that is gonna make it negative. And the other way around is typically non-bounded, because if the current reduced cost is positive, that solution is not optimal. If you're making it greater, nothing's going to happen. But you can't make it negative by making it larger. So that's it. But the interesting case is when you have a basic variable, because then when you're messing up with CB is affecting all of the variables reduced costs, not just the one you playing with. So let's say that Cj is the coefficient of the L basic variable. So it's just one of the basic variables. So CB becomes this vector where the component associated with L changes by delta. So all conditions get affected because this whole thing gets affected. So how to look into that? Well, the easiest way is just, think about this as like the L entry on your B minus 1A matrix, because it makes it easier to think what it is. And then, you're comparing, you have to compare the influence on all the other reduced costs, with exception of the one you have at hand of that variable that is changing. So basically J is changing, and we have to make sure we have a look at all coefficients associated with all the other I variables, to make sure they are not, they're not causing a change into the current basis configuration. So let's have a look at this in a numerical example once again. So exactly the same example as we had before. And if I'm looking, for example, at variations of variables x3 and x4, which were x3 is 12 and x4 is 0, basically what's going on is that if it decreases, it can decrease of more than 2 for this one, and it can decrease by more than 7 for this one, because otherwise these are going to become negative and then it's not optimal anymore. But they can increase as much as they want, and that's exactly what we're seeing here. Now, if we look at variations of, say, C1, so C1 is a basic variable, okay? So now we have a bit more trouble, because we have to make sure this condition still holds, right? And this, to analyze whether this condition holds, is the same as analyzing the following. So we have to see whether delta Q12 is less or equal than the reduced cost of variable x2. So let me mark these terms so you can see where it is in the tableau. So for this variable, this is, I'm comparing this, and my Q12 term, my elf basic variable is this. So I'm looking at this row. Probably need a different color. So I'm looking at this row. So these are my Q's as from the what we were saying before, and this would be my Q12, which is 0. So it gives me nothing. Now, when I look at x3, this is my reduced cost, and this is my Q13 right there. Let me mark this in blue. So I get this condition, right? This term here is minus 3. So this is 2. And then when I divide by minus 3, I get that. And last, when we look at this term, and this is the term I'll have to look at as well. And then I get this condition that is right here. So that is 7, and that is 2. And then I get less or equal than 2. Yeah, and because I only have a greater than equal than condition and a lesser equal than condition, then my very permissive the permitted variation on C1 is minus 2/3 and 7/2. So if C varies within this range, minus 5, minus 2/3 and minus 5 plus 7/2, my bases remain optimal. And that's about it. Right. So, well, if not, then it means that my optimality condition is broken, and this is a suitable candidate for primal simplex because it's a feasible solution that is not optimal. And that's it. Right. So we'll stop here, and next we'll look into this notion of cones and extreme race and how we use duality to derive some of these important results coming next. So thanks for watching, and see you in the next video.